Okay, hi everyone. I'd like to show you all a really handy fact, which is going to unite several types of problem-solving examples that we've done so far, and it also generalizes it more broadly to much more situations than we've seen so far. Really neat little fact, and then once we've got that fact established, then I'm going to show you how that fact applies to a couple of old exam questions, which I think is always good to see. Okay, so let me share my screen and we will dive right in. So there's lots of questions that we've seen in the past about linear independence or span, in which we have to take a look at linear combinations, and specifically how we've understood linear combinations in these different situations depends, right? So sometimes we're looking at linear combinations of vectors in Rn. And you've noticed that when you take linear combinations of vectors in Rn, what you end up with really is you're taking linear combinations in coordinates. Okay, likewise, now sometimes we're looking at linear combinations of polynomials. And you have probably noticed as well, now these are very different looking questions, but when you take linear combinations of polynomials, you end up effectively taking linear combinations in the coefficients of those polynomials. And then we argue from there. And then lastly, sometimes we're looking at linear combinations of matrices. We've seen fewer of these. Nevertheless, when you take linear combinations of matrices, in effect, you find those linear combinations take place in the elements, position-wise in the elements of those matrices. Okay, so in all cases, though, the reason that this is helpful is because these two of these kinds of things are equal if and only if these things are equal, right? Two vectors are equal if and only if their coordinates are equal. Two polynomials if and only if their coefficients are equal. And of course, two matrices if and only if the elements that make them up are equal. Okay, so punchline then, we can turn a question about linear independence and span of these kinds of vectors in different contexts to, in fact, what ends up being systems of equations, right? By equating all the coordinates, we get a system of equations. By equating all the coefficients of the resulting polynomial, we get a system of equations, and likewise for elements of matrices. So these facts, the facts that linear combinations of these kinds of vectors show up in the kind of coordinates in some sense, different in every context, allows us to turn hard questions into systems of equations, which of course we know how to do. Okay, so each one of these we've dealt with sort of separately, right? We spent time talking about linear combinations of vectors and independence of vectors in Rn, and then we had a separate discussion talking about how you do the same kind of thing for polynomials, and then in the few examples we've seen of matrices likewise separately. So we've dealt with these sort of ad hoc, but good news, these all are really special cases of a general argument that we can make. And that's what I want to show you all here. I want to unite all three of these examples and extend further with this theorem. So very nice little theorem. There's not that much to it, really. There's a bunch of algebra on the page you have to look at, but let's just think about what this says. This says the coordinates of a linear combination are the same as that same linear combination of the individual coordinates. In other words, linear combinations are computed coordinate-wise. Now, we've heard this phrase before, linear combinations are computed coordinate-wise. This phrase coordinate-wise, we've understood only sort of in the Euclidean context. It's kind of a flashback to multivariable calculus when we first saw vector operations, vector addition, etc. But this theorem, as it's being stated, is coordinates with respect to any basis. It doesn't have to be the standard basis in Rn. It could be any basis in any vector space, right? Okay, so any basis in any vector space. So I'm not going to write out the complete proof of this fact. I am going to outline it for you, and I think it'd be a great exercise for everybody to take a little time and try to prove this on your own, fill in the details of the outline I'm about to show you. It's very brute force. There's no sort of tricky machinery in this. It's a matter of kind of writing it all down and confirming that, yes, indeed, it works the way we would expect and hope that it works. And here's how you do that. We're just going to say, look, these vectors that we're interested in, I mean, if you have a basis, right, given a basis, those vectors that we're interested in are going to be some linear combination of those basis vectors. Let's give those coefficients names. And with that, we can proceed to just write out a few things. For one thing, you can write out the coordinates of each of these vectors that we will eventually be taking combinations of. Their individual coordinates, well, you can see them right here, right? These are the individual coordinates. So you write those down. Next, look at the other side of the equation. Take a linear combination of these vectors, right? This is these same vectors. Take linear combinations of them. You're going to have to multiply out and collect all the terms together. Once you have that with all the terms collected together, you can write down the coordinates of that linear combination. So write out those coordinates as well. And then you can just directly observe, having computed this and having computed these, you could brute force check that this linear combination of these things is equal to the coordinates of the whole. It's just a matter of writing it all down and multiplying it out. Okay, so this is a nice exercise for students to do on their own, and the result is to prove the theorem that we just stated. Okay, so again, repeating, once you have a vector space and a basis, coordinates, linear combinations are computed coordinate-wise, right? Okay. All right. So how is this useful? What is this? Why does this help us? So let's think about this old exam question. This is from the academic year 2012-2013 spring semester exam 2, question 1. And in this question, we've got a list of 5 functions here, and they're kind of ghastly, right? And the question is, we want to know if this collection is linearly independent. Okay, and explain how you know. Now, there are 3 ways that one could answer this question. One is to use a dimension argument. And as of this recording, we have not yet introduced dimension in this course. So we're not going to use the dimension argument. It's a nice way to do it, and arguably it's the easiest way to do it, but not going to make that argument here. Another way to do it is to use something called the Wronskian, which I typoed here. The I and the A are transposed, typo. But the Wronskian is another thing that we haven't introduced at this point in the course. It is technically a way to answer this question, but it's highly undesirable. And you'll see why when you see what the Wronskian is. That'll be for a later date. Okay, so we're going to do the third method, which is to use coordinates, to use our brand new theorem. It ends up being actually a really nice way to solve this problem. Okay, so the first thing we need to recognize is that we are actually doing business inside of a vector space. Now, it doesn't leap off the page at us. It looks like we're doing trig, right? But we're not doing trig. All of these functions can be thought of as linear combinations of sine and cosine. Now, how do I know that? Well, that's the good old angle addition formulas from high school trig. And let me, quick digression. I know that a lot of you have not maybe memorized those formulas, or maybe you did in high school and then have since forgot them. they're going to be really important in Math 216, especially once we start getting into differential equations, which will be coming up pretty soon here. But they also tend to come up surprisingly often in other areas. So while it may be the case that many students in many majors don't necessarily need to have those formulas memorized, and maybe that's why high schools don't require them. In this course, and for students going into engineering, it's really useful. So they are required in Math 216. Make sure you know the angle addition formulas, specifically angle addition formulas for sine and for cosine. You don't need to bother with the angle addition formulas for, tangent, cotangent, stuff like that. Just sine and cosine, you need to know those. Okay. Right, so I'll leave it as a quick exercise for y'all to plug in each of these. You'll notice it can be thought of as an example of angle addition. Multiply it out. Each one of these will reveal itself as being a combination of sine and cosine. Okay. Okay, so we are doing business inside of a vector space. And furthermore, this handy little pair of vectors, sine and cosine themselves, are a basis for that vector space. It's actually surprisingly easy to see this. How do I know that they're a basis? Well, I need to check that they span the space. How do I know that a pair of vectors spans their span? Well, sort of by definition, right? Of course they span their span. That's what a span is, right? I guess we're using span as a verb and then also span as a noun, but that's the usage. So this is an immediate consequence of the construction of V. Now, how do we know that they're independent? Well, this is a special case of the fact that there are two vectors in this list. And when you're looking at two vectors, there's only one way that a pair of vectors can be independent. And that is, you need neither one to be a multiple of the other, right? Because there's only so many different kinds of relations you can have, and there's only one that could possibly be a linear combination of the others, but there's only one others, so it's other, so it's just one would be a multiple of the other. It's really convenient how simple it breaks down to. Is one of them a multiple of the other? For these two, it's clear neither one is a multiple of the other, therefore independent, and therefore we have a basis. All right. Okay, let me observe real quick before we go on. If we were making the dimension argument, which again, as of this point in the course, we don't know how to do yet, so we can't. But if we were, we'd still have to do both of these, right? So where my coordinates argument that I'm about to show you, where that diverges away from the dimension argument, is sort of now. Okay. Okay. So I want to decide if my list of 5 functions is independent or dependent. And so we look for relations. This is what a relation would look like. And as usual, just like with vectors in Rn, just like with polynomials, just like with matrices, whatever vector space you might be having to look at, I need to see, is there a significant relation, or is the only relation the trivial relation? So I'm looking at this equation here, and where do I go with it? I'm going to take advantage of our new theorem. Our new theorem is about coordinates. So we're going to take our equation that we're actually interested in. We're going to look at coordinates with respect to beta. Right? Notice that's all we did here. I just took what I have in the previous equation. I just took coordinates on both sides with respect to beta. And here's where we use our theorem. Our theorem says that the coordinates of a linear combination are that same linear combination of the individual coordinates. Okay. And all of a sudden, the problem has become a much easier problem. Let's think through the details. Why is the problem a much easier problem now? Let's look at these individual coordinates. What might be, for example, the coordinates of F1 with respect to beta? Well, don't forget what beta is. Beta is a list of just 2 vectors. Right? So coordinates is going to be just, well, it's going to be a pair. It's going to be two numbers. And so each one of these is going to be a couple of numbers, ordered pair. I'm going to say A, I, B, I for the ith one of these functions. You know, I goes from 1 to 5. So that applies to each one of these. Each one of these, you know, coordinates with respect to beta is some numbers, and you can work out those numbers if you want. We're not going to, because in this case, it turns out that it won't matter. We'll see why in just a moment. But a couple of numbers, and now our problem is really translated into something very familiar. Here, I'm looking at a linear combination of 5 vectors in R2. Right? And this now is just like a lot of problems that we've seen in the past. You can write out this as 2 separate equations. You've sort of got the top equation and the bottom equation. So this vector equation is the same as a system of equations, which I can write as an augmented matrix. And now it's just, it's chapter 1 arguments, right? Clearly we have only 2 rows. So there's at most 2 pivots. But wait a minute, there's 5 columns. Oops, 5 columns, but only 2 pivots. That means that there's going to be free variables. We know there's no contradictions. This is homogeneous. So there's got to be at least 1 solution. And we also have at least 3 free variables. So therefore, there's infinitely many solutions. Therefore, there's a significant solution, right? Easy rank argument. Once you know that there is a significant solution, that means that there is a significant relation among the original 5 vectors, and that means that original 5 vectors are dependent. Okay, so that's how that argument works. I want to point out where and how the big theorem did some magic for us. Here's our new big theorem that coordinates of a combination are combinations of individual coordinates for any basis, right? So in other words, linear combinations are done coordinate-wise. Notice in the algebra, in the argument that we made here, where that showed up, we were looking at a hard problem of how do I deal with linear combinations of these complicated kinds of functions. It's not clear what those are, how that works, right? And then we translated that into, well, easy question, right? This is a chapter 1 kind of question. And the thing that made that possible was the theorem, right? Translating the coordinates of a combination into that same combination of the individual coordinates. Right, that's what translated the hard problem in purple into the, well, much more familiar problem in green. Okay. All right, so I think that's a really nice argument. It's a nice application to an old exam question. Again, soon we will see that there is a dimension argument on this. Let me show you now, however, another old exam question for which the dimension argument doesn't work, right? Okay, so here we go. This is here. Now, though, I guess I should probably show you which exam question this is. This is from 2020 fall and exam 1. And we are looking at question 5. Okay. All right, it's a 2-part question. The first part, I'm not going to spend a lot of time on. The first part said, well, both parts pertain to this vector space. Notice this is an unfamiliar kind of a vector space. In the notes, we don't really talk about this kind of a vector space where you have an ordered pair, not an ordered pair of real numbers, but an ordered pair of functions, real valued functions. And we haven't really done anything with that up to now. So we're in uncharted territory. The first part of the question, though, that I'm not going to spend any time on, is to show that, in fact, there's a basis. Now, this is details. It's a good thing to look at. Go ahead and give it a glance, but it's a standard sort of argument in establishing that something is a basis for a given vector space. What I want to show you is how to use that to answer part B now that we have a basis, right? I give you now a list of 3 different vectors. Notice each one of these is a vector in this vector space. We have this question, is that trio of vectors, is it independent or is it dependent, right? I claim a dimension argument will not work here. There is no dimension argument to be made. Likewise, the Wronskian wouldn't help us either. But a coordinates argument is still going to work, and it's going to work just fine. By the way, you'll notice on this old exam question, I gave students this fact to work with. That's our tool that we're using here, namely that the coordinates of a combination are that combination of the coordinates. Okay. So, okay, well, here's what we're going to do. Trying to decide if this list, here, let me circle them individually, trying to decide if this trio is independent. We need to look at combinations, right? Hopeful relation. Linear combination of these vectors that hopefully, fingers crossed, add up to 0. We need to decide if the only relation is the trivial relation, or we need to know, could it be, perhaps, might there be a significant relation? So that's our question. And again, notice, just like in the previous example, we find ourselves looking at a hard vector equation that we don't really know how to deal with, right? I mean, how would I draw a conclusion about this? So what I'm going to do is use our basis, right? I'm going to say, we know I can take alpha coordinates on both sides, and I can rewrite the alpha coordinates of the combination as the same combination of the individual alpha coordinates, right? That's just using our new big theorem. So now we have a little bit of details to be dealt with, and this is, you just got to kind of take a look at it and think it through. But how am I going to find these individual coordinates? And I actually do need to know them for this question, and it's not that big of a deal. Let's look back up at our basis. Notice that our basis, the first 2 vectors in our basis are sine and cosine in the first entry. The second 2 elements in our basis are sine and cosine in the second entry. So we just need to count how many sines are there in the first entry, how many cosines are there in the first entry, how many sines are there in the second entry, how many cosines are there in the second entry. And those will be our individual coordinates. So there's 1 sine in the first entry. There's -1 cosine in the first entry. There's 1 sine in the second entry, and there's 1 cosine in the second entry. So it's just a matter of looking and counting, right? I mean, I gave myself a very convenient basis to work with here. Always a good idea if you have the choice, right? Pick yourself a very convenient basis, and thus finding these individual coordinates is relatively easy. So again, now likewise for the other vectors involved, and notice that what we've left ourselves with then is that this hard question that I don't know how to I don't even have a foot in the door to answer. I've now translated that into a very familiar vector equation, which is a system of equations, which is a matrix equation, which I can solve by row reduction and the usual methods. So some tedium to be done, and again, this is it's just a matter of doing it. No big deal really. That this equation turns into this augmented matrix, which we row reduce, yada yada yada, and then we draw conclusions from the reduced echelon form. And what you see here is we have a pivot in each column. Because there's a pivot in each column, that means we have unique solutions. Therefore, the trivial solution is the only solution. Therefore, there's no significant relations, and therefore that list is linearly independent. So now there's, again, the details at the end here, blah, 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 right? But where did the magic happen? Where did we really solve the problem? And again, it's right here. Right? That's where we turned the original question. I don't have a way to deal with. We turn that into, well, a familiar, I mean, a little tedious maybe, right? But still familiar and totally doable question of row reductions. And that thing that allowed us to do that is this theorem. This theorem that we just talked about here. Okay. All right, so I think this is another nice example. Again, notice you cannot do this question here with a dimension argument, and you certainly can't do it with a Wronskian. So coordinates, very nice, powerful tool. Okay, so I just wanted everybody to see that. I hope this was useful. It is a neat trick. You've seen now a couple of old exam questions where it turned out to be really important. Anyway, depending on how you look at it, could have been viewed as really important. And hope you'll find it important too. Okay.